Alrighty, welcome back, Math 131. We're on the home stretch now. I think we'll only have, if I counted up correctly, 21 lectures. So I think there are only 3 more with the testing, with one test included. So we're on lecture 18. Yesterday we actually did a little U substitution with a definite integral back in section 6.1 or 2, somewhere in there, 6.1 I think. But the section in 9.3 shows you another way, which is kind of an option for you for doing U substitution, and I'll show you that option, and then you can do whatever you like. So we'll go to 9.3. Also, that kind of gives us a review of integration by substitution. Then I've already started to give you a little bit of insight to section 6.4, which is finding the area of regions bounded by curves. I put that in, I kind of put that on you yesterday, but that's actually 6.4, so that after you see it a couple times, then it gets easier and easier as long as you integrate. 6.4, areas of regions bounded by curves. There's a lot to that application in that other applications for integration a lot of times rely on getting the area of a region. For example, I'm going to see if you can just visualize this. If this were your region that you were getting the area of, and if I rotated this around, like with one of those little little party favors that when you open it up, it kind of crinkles around in a honeycomb thing. Do you know what I'm talking about? Those. Okay, didn't y'all ever have little pumpkins that were flat and you unleashed it and went around and it was a pumpkin? Okay, so another application, and it's actually in your book but not a requirement of Math 131, is finding the volume of a solid of revolution. And so once you get the area of a region, what you can do is you can rotate it about an axis and come up with a solid. So this would have just been some kind of rectangular looking solid. Would have been around the outside. That, or finding, and these are not applications you're getting to, but you just have to know area of a region to be able to link onto that to get some other applications. If you wanted to find the little point in this little plane that would make this balance, it's called the center of mass. That involves learning how to find the area of a region. If you hear on the radio things like the average temperature today was, okay, what happens is you would take a function and you'd be looking for the average Y value, the average temperature during the day, and it's a plotting of a lot of points. That has to do with a definite integral summing it up. The length of an arc, how long something is that's not a straight line, has to do with definite integral. There's just tons of applications for definite integral, but there are also tons that relate to, if you get the area of a region, doing something with that region to find something else. And so we're just getting the basics here, areas of regions bounded by curves. And that's a very important application, and we are going to go there. All right, the first thing, though, is sort of a review, and I'm telling you one new thing in section 9.3. Because we know how to do U substitution and we know how to evaluate definite integrals, just going to add on a little bit. I have gone to the exercises in section 9.3, and I have picked out some problems I want to do, but if you see something you really want to do, we can do that too. I have picked out number 4 as one. And I've tried to pick out a variety so that we get a good review as we're doing it. The definite integral from 0 to 1, 2x over the square root of x squared plus 1. This is page 465. And as soon as you look at the integrand here, can you tell me what form of substitution that's going to fit? U to the r. You are very good. And I've also picked out problem number 11 for us to do. And as soon as you see problem number 11, do you know what that substitution form is going to be? 1 over u. I am so proud of you guys. And what about number 13? What form does that look like? E to the u. So half the battle is knowing what form does it fit and then getting there. All right, so I'm going to start with problem number 4. We're going to work it, quote, the way we did it yesterday with the u substitution and putting it back. And then I'm going to offer you another method, and then you do like you want to. All right, so question number 4 on page 465. Like on the test, I don't say, you must do it this way. It's just a choice, whatever you want to do. All right, so we're on page 465, and we're at problem number 4. And it's the integral from 0 to 1. And I'm going to write that as x squared plus 1 to the negative 1/2 times 2x dx. Okay, because we already know that that denominator has to come up in the numerator if we're trying to make it look like the integral of u to the r du. Okay, why don't you take a half a second and go ahead and work this, and don't look at me. You do it yourself, and then I'm going to show you a second method. How am I doing?
Where'd that 2 come from that you put in front of the u?
When you add 1, you also have to divide by that number, right? So divide by half is multiplied by 2. Okay? All right, I'm going to pick up our method and go. You had already told me it looked like a u to the r, so your u is x squared plus 1. And when you take the derivative of that, that's 2x dx, so the 2x dx is the perfect du. So there's a u to the negative 1/2 du. So it's a u to the r, so I'll add 1 to the exponent, which makes that a u to the 1/2. Divide by half, invert multiply, is times 2 plus c. Now, what I am calling your attention to is when I converted that integrands to u's, I didn't put 0 to 1 because 0 corresponds to an x and 1 corresponds to an x, and I've converted this to u's, so 0 does not correspond to u and 1 does not correspond to u. So I just converted to the u's to get the integration. And then I substituted back. Now, when you're integrating, evaluating a definite integral, I can put the plus c in there, but it's going to always cancel out when you put in upper value minus lower. So now to evaluate, we have 2 times the square root of 1 squared plus 1 minus 2 times the square root of 0 squared plus 1. Just evaluating the definite integral. So it looks like we get 2 square roots of 2 minus 2. Okay, and that's a perfectly great answer. All right, is that good? All right, now in 9.3, they offer an option. I'll just call it an option. So this is really your option. And the option is this. once you make your u substitutions, could you not also substitute in terms of u? So the option is that when I come down here and I have the integral of u to the negative 1/2 du, why not go ahead and change these values for x in terms of u? Then you would never need to go back. So right here, when x is equal to 1, what would you say u is equal to? 2. So I'll replace that 1 there with a 2, and that actually matches up with what u is. When x is equal to 0, u is 2. When x is equal to 0, u is equal to 1. So now, if I put limits on my definite integral with the du, I'm saying u is ranging from 1 to 2. So now, when I integrate this and get u to the 1/2 divided by 1/2, which is multiplied by 2, I can say, and my u ranges from 1 to 2. All right, and when we substitute that in, we're going to get 2, that's the square root of u, square root of u, which is 2, minus 2 square roots of 1, or 2 square roots of 2 minus 2. And what basically happens here is you saved yourself a step. You didn't have to convert back to x's and substitute with respect to x. You could just stay with your u's. All right, so it saves you just a little bit of effort. You like the other one better? This way better. Okay, so it's just an option, whichever way you want to do it. Let me.
Are you going to ask us the old method on this, or like, are you going to tell us which method to use?
Okay, his question was, am I going to tell you on the test you must do our old way or you must do the 9.3 way? I don't tell you. I just give you the problems and you make your own decision. Some people like to do this. Some people don't like to do it. So it's whatever fits your personality, you go for it. Okay? All right. So because this is in section 9.3, I will probably work my problems this way. You go with whatever you like to do. All right, any questions on that? I flipped fast. Everybody good? All right, let's do problem number 11. You're going to, this is number 11, and we're on page 465. Problem number 11, 465, and it's the integral from 0 to 1, x over x squared plus 3 dx. Okay, how am I doing on my substitution? Does it substitute to 1 over u, 1/2 du? Okay, when you took the derivative of the u, you get 2x dx. Don't forget to look. In your integrand, you have an x dx. So we multiplied both sides by 1/2. Is that good? All right, now I'm going to go with the 9.3 section. When x equals 1, my u is equal to what, 4? 1 plus 3 is 4. When x is equal to 0, u is equal to 3. All right. Now that says that my u values are ranging from 3 to 4. All right. So when we integrate, we will get 1/2 natural log absolute value of u evaluated from u equal to 3 to u equal to 4. So we'll substitute in. And since 4 is a positive number, we really don't have to use absolute value here. And u is 3. We don't really have to use absolute value. But if in doubt, do it. Don't ever just go make a change. So it's 1/2 natural log of 4 minus 1/2 natural log of 3. And because we're having great fun, let's use some of our properties of logarithms and see what this simplifies. Let's just simplify this, because I bet the back of the book's not going to look like this. All right, what are you going to do with that 1/2? Okay, so that's the log of 4 raised to the 1/2 minus the natural log of 3 raised to the 1/2. All right, what's 4 to the 1/2 power? Square root of 4, 2. So we get natural log of 2 minus the natural log square root of 3. All right, what does your properties of logarithms say when you got the log of 2 minus log of square root of 3? Divide. So this would be natural log of 2 over square root of 3. And that's the best answer. Best answer there. Okay. Many times, you know, the problem just says integrate. And if you integrate, this is probably just fine right here. But it probably is not going to match the back of the book. Okay. And this is better. This is a better answer. All right. How's that, everybody? Good? Everybody get it right? Any questions? When you did it the old way, did you get it right? What did you miss? Like this part? Okay. What are my good instructions? After you find du, what are you supposed to do, everybody? Look both ways at the same time. Okay? Don't forget to look both ways. All right? All right, last integration problem so that we're having some good reviews. We're looking at problem number 13, and this is page 465. And we're integrating from 1 to 3. And we have x squared e to the x cubed dx. Integrating from 1 to 3, x squared e to the x cubed dx. Okay, is your substitution come out to be 1/3 e to the u du? Yes, the derivative of x cubed is 3x squared dx. When you look up in your integral, you got an x squared dx. So x squared dx is 1/3 du. Everybody good so far? All right, I'm going to send my limits on my integral sign to in terms of u. When x is exactly equal to 3, u is equal to 3 cubed, which is 27. And when x is equal to 1, u is equal to 1. Everybody good? All right, so we will get, that's the hardest one to integrate, right? If you integrate e to the u, you get e to the u. All right, so it's 1/3 e to the u, and we're evaluating from u equal 1 to u equal to 27. So we have 1/3 e to the 27th minus 1/3 e to the 1st. And we would just stop right there, unless you wanted to factor out a 1/3, but that would be about all you could do. Okay? Is that what you got either way you do it? For those of you who did it the other way?
I didn't quite get why 1/3.
The question was, where did the 1/3 come from? When you took the derivative of x cubed, did you get 3x squared? When you looked up there, all you saw was an x squared dx. So you had to divide both sides by 3 or multiply through by a third. So x squared dx is exactly 1/3 du. Does that help? Everybody good? All right, I really work you over on substitution on your test because that's a major important thing that you can do. All right, let's go to problem number 24. Problem number 24. All right. The other examples that we just did, the instructions were to evaluate, and that was just a Nike commercial, right? You just did it. All right, but in problem number 24, it says find the area of the shaded region. And it gives you the graph in blue here. The line's in blue and then it's shaded. Y equals minus x square root of 9 minus x squared. All right, and we're supposed to find the area of the shaded region. All right, what we're going to do is just set this up. We're not going to solve it because I need to, well, we could solve it. What do you want to do? Solve it or just set it up? Name it. Solve it. Okay, we will solve it. All right. When you see this, yesterday I encouraged you to put in what I call little elements of area, so that the little element of area is just a little rectangle. And you need to be able to see the top of the rectangle and the bottom, because anytime you need the height of something, it's top minus bottom, right? If something were up here and something were here, and you were measuring from this desk, you get the height up to the top, and then you would subtract off the height up to the bottom, and that's why it's top minus bottom to give me this part right here. So if you'll put in your little element of areas, you can see where the top of your little rectangle is, and you can see where the bottoms of your little rectangle are. And you notice that in this second quadrant here, the blue curve is on top. That tells you height in terms of y. And the bottom curve is the x-axis, which we know is the equation y equal to 0. And then once you pass the intersection of the x and y axis, now wherever you put in a little rectangle, the top curve is the x-axis and the bottom curve is the y equals minus x square root of 9 minus x squared. Okay? So when we get ready to integrate, remember we're going to sum up. So let's start right here. Well, how do I know what that number is so that I know what value of x to start summing up over? Okay, it's the x-intercept for this curve, right? And where x is equal to 0 is, where the x-intercept is, y is equal to 0. So we would have 0 equals minus x square root 9 minus x squared. So this is already factored for me. I have two factors multiplied together, the negative x times the square root of 9 minus x squared, where this is set equal to 0. So minus x equals 0, or the square root of 9 minus x squared equals 0. Okay, well, minus x equals 0 means x is 0, and that's that place right there. Right, that's where x is 0. All right, now how do you solve this square root here? Square root of 9 minus x squared equals 0. You can square both sides, and you get 9 minus x squared equals 0. Just square both sides of the equation. And you can factor here if you want. 3 minus x times 3 plus x equals 0. That's the difference of two squares. So you could factor. Set each factor now equal to 0, so x is equal to 3 or x is equal to negative 3. So this x-intercept here is obviously the negative 3, and this x-intercept here is obviously the positive 3, just by location. Okay? All right. Now, I would like for you to set up the definite integral that's going to give me the area of those curves, and then we'll check it. Set up the definite integral. You're going to sum up, start right here, all the little rectangles to here, then pick up here, see what you get. All right, let's see how we're doing. Remember, the integral sign's kind of a little squished out S here. So I'm going to start summing up, and I'm going to start over here, putting in all the little rectangles I can, as long as every little rectangle that I can, which is called a little element of area, I have the same top curve and same bottom curve. So where am I going to sum up from the beginning? Negative 3 to 0. Right? I'm going to put in all the little rectangles I can, because starting over at negative 3, the top curve is blue and the bottom curve is the x-axis. All right, so the top is minus x square roots of 9 minus x squared. I'm just going to put in every little step. Minus the bottom curve, which is 0. So that is the height of each of those little rectangles. The y value is height, and then the width is dx. All right. How many are good there? Good? Okay. The dx is important because that is width. And also that tells you what you integrate with respect to. And it has to be there because that's telling you what the variable is and what the limits are with. Okay. Everybody good to there? All right. Then we notice that at 0, on this side, the top and bottom curve change no matter where I put in my little element of area after 0. So I'm going to pick up at 0 and go to where? 3. And the top curve this time is 0 minus the bottom curve, which is minus x square roots of 9 minus x squared. So that's top minus bottom, and that tells you how tall it is. And you're looking for area, so that'll give you a positive value. That's the height, and the width is dx. How's that, everybody? All right. So I'm going to integrate it, you're going to integrate it, and then we'll look at our work. and make a comparison, okay? So you go for it, and I will too. Whoops. All right, let's see how I did on the first part compared to you. I was about to make a mistake. All right, first of all, I just sort of cleaned that up because there was no need to keep in the minus 0. So we have negative x 9 minus x squared to the 1/2 dx. Okay, interrupt me if I need to say more. All right, it looks like a u to the r du type problem, so I'm letting the u be 9 minus x squared. So that's u to the 1/2. I take the derivative of du, and it's minus 2x dx, and I didn't carefully look both ways, and I was about to make a mistake. I saw there was a minus x there. So really, I just multiplied through by a positive 1/2 after I realized I made a mistake. So the minus x dx is positive 1/2 du. All right, don't look at my limits yet. Is that substitution okay? All right, then I like to go ahead and change the limits so I don't have to substitute back. When x is exactly equal to 0, u is equal to 9 minus 0. So where x is 0, u is 9. When x is negative 3, 9 minus the negative 3 squared. Negative 3 squared is 9. 9 minus 9 is 0. So u is 0. So I've changed my limits on my u. Excuse me?
When x is 3.
When x is negative 3,
Oh, 3. Oh, the next one.
next one over here. I haven't done that one yet. All right, so I'm going to go from 0 to 9. So when I add 1 to my u to the r, add 1 to it, that makes it to a 3/2 power. Divide by 3/2 is multiply by 2/3. Are you forgetting that, Carrie? Okay. All right. And then 1/2 times 2/3 simplifies to a third. So just sort of change that. And a 3/2 power means a square root of u and then cubed. 3/2 power, square root of u, and then cubed. I'm using the little rule a to the m over n is the nth root of a raised to the m. It's also the nth root of a raised to the m underneath, but normally it's easier to simplify if you use it this direction. All right, so we put a 9 in. We'll take a square root of 9 and cube it. Square root of 9 is 3. 3 cubed is 27. 27 divided by 3. And then, of course, that's a 0, so that knocked out. 27/3 is 9. All right, everybody good?
We really don't have a calculator on this part.
No, absolutely not.
No.
That's algebra. You are in calculus, and you are expected to know your previous skills. What chapter in the book were you supposed to spend Saturday nights on? Chapter 0. This is chapter 0, so go back. All right, let's do the other side real fast. That should go pretty quickly. We're going to integrate. I have the same u. This time, if my u is 9 minus x squared, du is minus 2x dx. And now when I look, it was minus a negative up there, which made that a plus. So now I am going to multiply by negative 1/2 because that was a positive x dx. All right, so I now have times negative 1/2 with the du. Okay? All right, let's get our limits on our integral. When x is 0, u is 9. When x is 3, 9 minus 9 is 0, right? Okay, so we go from 9 to 0. What's going to happen is you're just adding this direction instead of the other way. It's going to work out, should work out. And the deal is here, that negative right there is going to switch it around.
So you have to put the one that it corresponds with is the
Yes.
x equals 0.
Yes,
and
yes.
9.
This 0 corresponds to u at 9, and this 3 corresponds to u at 0.
It does.
Yeah, if you switch it around, it really reverses the sign in your answer, because remember, it's top number minus bottom number. All right, so we have, integrate this, minus 1/2 u to the 3/2 times 2/3. I know that looks weird. U equal 9 to u equal to 0. Okay, so now we'll substitute in. We get negative 1/3 square root of 0 cubed. Put in the 0. Minus, that's going to be a negative 1/3 square root of 9 cubed. So the first part is 0. Now you have minus. The square root of 9 is 2. 3. Whew. Square root of 9 is 3. 3 cubed is 27. So we have minus 27 over 3 minus a negative is going to be a positive 9. And you really expected that to come out to be a positive 9 if the graph, it looked like the graph was pretty symmetric. So you expected the area above the curve over here to be the same as the area of the curve below the curve over here. It looked symmetric, looked like symmetry there. Okay? All right, that was weird looking, but you have to follow your limits, your values. All right, everybody good? All right, let me tell you which problems in 9.3 you cannot do because you skipped section 9.2 until 230, Math 231. So I'm just going to look down these because you need to practice. You cannot do, actually you can do, but we didn't do any like it. Number 12. You cannot do 14, that's integration by parts. Number 12 you really could do, and if we had a lot of time we might go back and do that. All right, you can do 15. You cannot do 16. Okay, so you cannot do 14, 16. You could do 12, but don't worry about it. We don't have derivatives of trig functions and integration in this class, so forget 17, 18, 19, 20. Well, you might as well forget the rest of those. 21, 22, 23. Forget those two. All right, so you want to work problems 1 through 13 here, okay? And then 25, you can do 25, so please play with that one, okay? 25. All right, let's head back to section 6.4. Do you need to stretch? Just put your brain through a lot of work. This is 6.4. Using the definite integral to find the area of regions bounded by curves. I can't think of a test or final exam that did not have this question on it. Does that tell you how important that is? Very important. Very important. All right. I'm just going to sort of give you the theory of this. That's a theory, T-H-E-O-R-Y. The theory behind this, and then we're going to go for it. Basically what happens is you're going to have some function f of x. And you're going to have some function g of x. Now everything we've done so far, the bottom curve was along the x-axis. But the bottom curve doesn't have to be along the x-axis. It could be up here. And so we'll need to find out where these curves intersect. And that was a good old pre-calculus course, finding the intersection of two curves. Remember you set the two functions equal to each other and solved. You did that in pre-calculus. So we find out where they intersect, and then you say, I need to sum up all the little rectangles that I can put in here. And these are my little elements of area, which are just little rectangles, because I'm always looking to see what curve is on top and what curve is on bottom. And no matter where I put a little element of area, a little rectangle, the top curve is always the black one in this case, always the black one, which is f of x, and the bottom one is the g of x, g of x. Okay, so when you say so to find this area, I bet every one of you could tell me what to do. What would it be? Summing up from where to where? A to B. And which one is the top curve? F of x. All right, now remember, f of x is a y value. So you've really measured from the x-axis up to the black curve, right? That's how high that is from the x-axis. And then we will say minus, oh, you were going to tell me, g of x. Well, g of x is a y value, and that's how far you are here. That's how far you went up from the x-axis to get to that y. So when you say f of x, take away g of x, that's going to tell you how high each little rectangle in there is. Does that make sense? All right, so it's always, always, always. This is an always situation when we're working with x. It's going to be top minus bottom. Top curve minus bottom curve. And what else is missing here? Dx. Dx is that little itsy bitsy width right there with respect to the x-axis. Top minus bottom dx. And if I sum that up, that will give me the area of that region right there. Okay? Oh, it's easy because I already put you through torture yesterday, right? All right, so now what's the deal? We have to be able to draw the curves. We need to be able to find the point of intersection and decide top curve and bottom curve. All right, so here's the first example. All right, the instructions on the test usually say something like find the area of the region bounded by. And I usually say graph, find points of intersection, shade bounded region. That's half the battle of knowing how to set it up, is being able to graph it, find your points of intersection. Really all you have to do is find the x-coordinate of your point, the x-coordinate. Shade the region so that you know what area you're talking about, and then set up your definite integral. Okay, it's going to be bounded by. Here's our first example. Y equals x squared plus 1, and y equals x plus 7. All right, so you know that you need to know how to graph parabolas, straight lines, y equals square root of x, those basic functions. All right, without your graphing calculator. You worked on this in pre-calculus. All right, they don't have to be perfect graphs, but they got to be good enough that you can tell what's what. All right, as soon as you saw y equals x squared plus 1, what's that the graph of, everybody? Parabola. It's been shifted up 1. So you're just getting a feel for what it looks like. All right, so that's y equals x squared plus 1. Doesn't have to be a perfect graph. The only time you're going to have to really be careful is if it looks like the curves are on top of each other. So if you graph something and it looks like the two curves are on top of each other, what does that tell you need to do? Spread out your units, right? Spread them out. All right, that reminds me, I'll do one where that looks like that. Okay. All right. Y equals x plus 7. As soon as you see that, you know that's the graph of line. Y-intercept is 7. And the slope is 1. So you go up 1 over 1. Just trying to get a feel for it. Again, it doesn't have to be a perfect graph, but you got to be able to tell where they what the bounded region looks like. Okay, so a bounded region means enclosed by these two curves. So does everybody agree the bounded region's right here? Okay. All right, so let's put in our little element of area, because we need to put in a little rectangle so we see where the top curve is and where the bottom curve is. And you may want to put in several just in case the top curves and bottom curves change. But no matter where I put in a little rectangle, the blue curve is always on top and the black curve is always on bottom of my little rectangle. Does everybody see that? All right. Now, what have I got to figure out next? The intersection of those points. What is this value? And what is this value? All right, so how do you find out where two curves intersect without a graphing calculator? Set the two curves equal to each other. So we'll set the y's equal to the y's. So we have x squared plus 1 equals x plus 7. All right, this is a quadratic equation, so we know we want a 0 on one side. So we have x squared, subtract x from both sides, subtract 7 from both sides. And fortunately, this one is going to factor. If it doesn't factor, what are you going to do? Go into the quadratic formula. Yes. So this one factors to x minus 3, x plus 2. So they're going to intersect at x equal to 3 and x equal to negative 2. So this value right here is minus 2. This value right here would have to be 3. All right, you set up the definite integral, and then I'll pick up from there with you. All right, tell me what it is. You're going to integrate from negative 2 to 3. It says I'm going to start over here with little rectangles and sum them all the way up until I get to 3. And what goes on top? I mean, what's next? X plus 7. Be very careful with your parentheses. Top minus x squared plus 1 dx. That's your height, and that's your width. All right, so let's finish this one so we'll have it. The rest of these we're just going to set up. You can practice your integration. Main idea here is, can you set it up? Because now I know you already know how to integrate. All right, let me slide this up. And so we have the integral from negative 2 to 3. And it looks like we have x. And then we have a 7 minus 1, so we're going to get a 6. And then it looks like we have a minus x squared. All right, so I would encourage you to simplify in your integration first. And you may want to write this in descending powers. You do whatever you want to. Nobody says you have to do it. Okay, you might want to write that as minus x squared plus x plus 6 instead of having it out of order. All right, let's integrate. Just integrating term by term. If you integrate x, everybody, that's derivative. X squared over 2 plus, thank you, 6x minus x cubed over 3. And we're evaluating from x equals negative 2 to x equal to positive 3. All right, so let's substitute in the upper value. 3 squared is 9, so we have 9 halves, plus 6 times 3 is 18, minus 3 cubed is 27. 27 divided by 3 must be about 9. Is that right? Minus. Now we're going to put in negative 2. Negative 2 squared is positive 4. 4 divided by 2 is 2. Be careful with putting your brackets in because it's the upper value minus the whole thing with the lower value. Okay, 6 times negative 2 is negative 12. And then we got minus. Now, negative 2 cubed is negative 8. So we got a minus 8 thirds. Okay, negative 2 cubed is negative 8 over 3. So it's minus a negative 8 thirds, which I know is going to be positive. All right, everybody good? Arithmetic usually kills you, right? So does balance in my checkbook. So here we go. All right, 9 halves. 18 minus 9 is 9. Minus 2 minus 12 is negative 10. And then in here we have a plus 8 thirds. Okay, half of it is just taking your time to do it. All right, so we have, now let's remove the parentheses. So we're going to have a 9/2, and it looks like I'm going to have a 9 plus a 10. 9 plus 10, 19. And then I have a minus 8/3. Okay? All righty. So then you can decide what you want to do here. Probably get a common denominator. 9/2 minus 8/3. Common denominator is just 6, right? So 3, that would be 27 minus 16. Multiply this by 3 over 3, and this one by 2 over 2. Okay, what's that, 11? 11 over 6. So that will be 11/6. All right, and 6 goes into 11, what, one time? Okay, so that would be 20 and what, 5/6? Okay. And this would be the area. So the units is square units. Square units. This is 11/6 is 1 and 5/6. So 19 plus 1 and 5/6 is 20 and 5/6. Square units would be our area there. Okay? All right, I wanted to go all the way through one just to make sure we're good. All right. Let me do the problem I just thought of real fast, and then we're headed to the book. This is just going to be a setup because my concern is your graphing. All right, we want to just set up only the definite integral to find the area bounded by y equals x squared and y equals square root of x. And we're only going to look in the first quadrant, which is the only place this really is anyway. All right. Y equals x squared and y equals square root of x. I want you to set up the definite integral to find the area between those two curves. Okay, this is going to be, I'm going to push you a little bit because I'm watching the time. This is a situation where you're going to really need to spread out the units because where are these two curves going to intersect? 0, 0, and 1, 1. And if you've got them drawn too close together, you can't tell which is on top and which is on bottom. Okay, so when you can't tell which is on top and which is on bottom, we already know they're intersecting at 0, 0, and 1, 1. Okay, just set the two equal to each other and you'll see that. So what is an easy point between 0 and 1 we can take the square root of? One-fourth. Okay. 1/4. All right, so here's 1/4. All right, so I'm going to do the square root of x in blue, and I'll do y equals x squared in red. All right, so what is the square root of 1/4? 1/2. So we have this point right here. So I'm just going to try to connect the dots. That's y equals the square root of x. Now we want to use that same point because y equals x squared goes through 0, 0, and 1, 1. All right, so if I put a 1/4 in for x and I square it, what do I get? 1/16, and that's going to be way down here. So y equals x squared is going to follow these dots. Okay? All right, if you had just carelessly drawn this, as some students in the past have done, not you guys, but other people, when they graph it, they do like this, and they do like this, and then they can't see which is on top and which is on bottom because they're on top of each other. So whenever the curves are so close, you need to spread out those units. All right, so life is going to be great now. What's the definite integral? Okay, we're going to sum up from 0 to 1. And my top curve is square root of x. My bottom curve is
x squared.
X squared
Times dx.
Times dx. Thank you. You're
I
not gonna
remember
miss
that.
it. I know you're not going to miss it on the test, and I'll put a big check on your paper. All right, there's the definite integral. All right, I'm going to go to a problem from the book, and I'm going to have you select the one you want to do. I'm on page 354. Page 354. And we're going to look at problems. And let's do, pick an even problem here because you got the odd in the back of the book. So I'm on page 354. I'm going to let the group here tell me, do we want to, the instructions are find the area. Number 12, 14, 16, or 18. Which one you want to do? I hear a 18. Do I hear anything else? 16 is one of those you're going to have to spread out.
Let's do 14.
14 is pretty easy. What does a graph of y equal 3 look like? It goes this way, horizontal line. So that's just going to be a parabola that opens up with a horizontal line on top. All right, so you want to do 18? That looks pretty hard.
Yeah.
All right, let's do 18. All right. And we're just going to, again, set these up because we need to set up lots of problems today. All right, so this is page 354. We're looking at problem number 18. And we're going to set up the definite integrals to find the area y equals 4 over x bounded by y equals 4 over x and y equals 5 minus x. Okay. All right, let's see if we can make a sketch here. Let's graph the y equals 5 minus x first because that's really easy. What does the graph of y equals 5 minus x look like? Straight line. The y-intercept is 5. The slope is minus 1. So we're up here at 5, and you're going to come down 1 over 1. We're just getting an idea what it looks like. Okay? So y equals 5 minus x. Okay? All right. This is really y equals 4 times 1 over x. So what does the graph of 1 over x look like? Okay, that's your little hyperbolus. Your hyperbolus. All right, so 4 times it just means the y values are now being multiplied by 4. So let's just put a few points on this one. When x is 1, the y value is 4. I'm just putting a few on here. This is a intercept here of 5. Okay. All right. So when we know that you have a vertical asymptote, it's undefined at x equal to 0. All right, so just to get an idea, when x is 1, the y value is 4. Okay, and so the curve's going to come around like this somehow. All right. When x is equal to 5, the y value is 4/5. So that's that 4/5 right there. When x is 2, the y value is 2, and over here the y value is 3. So you know this curve's up here on top. Do you see that? A good place to pick is x at 2. When x is 2, 4 divided by 2 is 2. The y value here is 2 on the blue, but on the red, 5 minus 2 is 3. So this is up here at 3. So do you see the red is on top of the blue? Okay. All right, so it looks like we're going to need to worry about a point of intersection here. Let's see what we get. Set the two curves equal to each other. 4 over x equals 5 minus x. All right, we're not going to worry about multiplying through by x because x can't be 0. It's not part of the domain there. That's a restriction on the domain. So we'll multiply both sides of the equation by x. Okay, and when I do that, I'm going to get 4 equals 5x minus x squared. All right, so quadratic, let's carry everything to the left. X squared minus 5x plus 4 equals 0. Carried everything over to the left. X squared minus 5x plus 4 equals 0. Aren't we happy that this factors for us? That would be x minus 4, x minus 1. So they're going to intersect at x equal to 4 and x equal to 1. If you let x be 4, the y value is 1 here and the y value is 1 here. So it's going to intersect here at 1 and here at 4. Okay. All right. We see the bounded region between the red and the blue. So we're going to sum up from 1 to 4. See your little element of area in here? What's your top curve? 5 minus x. The bottom curve is 4 over x. And then we have dx. What are you going to get, by the way, when you integrate 4 over x? Natural log 4, natural log, absolute value of x. Okay, so you're going to integrate term by term. All right, any questions on that setup? All right, let's back up just to the, do you have a question?
Yes.
Okay.
How about if the curve line is given by, in terms of x, say x is equal to 4. If one of the curve is a vertical line, say x is equal to 4, how you make it set how you set up the equation?
Okay, the question was if you have a vertical line here, how would you set that up? I'm trying to think of an example. Okay, I got an example. Okay. Example. Find the area of the region bounded by y equals square root of x and x equal to 4. All right. Oh, and you'd have to say y equal to 0. So I get the x-axis in there. All right, so the area bounded by these curves. Y equals the square root of x looks like this. X equal to 4 looks like this. Y equal to 0 is the x-axis. Okay, do you see your bounded region right here? It's enclosed by all of those curves.
How about if the x-axis is not given, y is equal to 0 is not
Okay,
given?
well, otherwise that would be an unbounded region.
Okay.
Okay, you have to have it bounded to be able to find an area. Without the y equals 0, it just goes down forever and ever, so it wouldn't have an area. All right, and in this case, this would be a pretty easy setup, right? You would sum up from 0 to 4. The top curve is square root of x. Bottom curve is 0. And there, that's it. Okay? Thank you. All right, let's look at one more problem in here, and then I want to answer a couple of homework questions real fast. Okay, the exercises 5 through 10 are just a little different. It says find the area of the region between the curves. So it didn't necessarily mean that the curves were going to intersect. It's just telling you where to go with respect to x. All right, so you have all these answers to the odd in the back. So I'd like for you to pick problem 6, 8, or 10. You'd like to do 10? Everybody go with 10? All right. You want number 4? Number 4 is easy. We might do number 4. I'll look at the time. All right, so problem number 10. Okay, this is page 354, problem number 10. And don't forget to go through the section in the book. They've got a lot of good problems, and they've drawn them out for you and colored and helped you. I mean, it's good practice, the exercises. Number 10, y equals e to the 2x, y equals 1 minus x, and we're going to go from x equals 0 to x equal to 1. All right, I'm going to do blue, e to the 2x. I'll do green, y equals 1 minus x. Okay. If you can draw it, it's usually pretty easy. And we're only going from 0 to 1, so we might as well spread the units out here. All right, let's go with the easy one first. Y equals 1 minus x. What's that the graph of? Straight line. All right, let's just mark our 1 off here. So y-intercept is 1, x-intercept is 1. We've got a straight line coming through here. Whew. Okay, that's y equals 1 minus x. All right. What does the graph of y equals e to the 2x look like? What does the graph of y equals e to the x look like? Exponential function. And when x is equal to 0, what is the y value? 1. Oops, I meant to do that in blue. Okay, when x is equal to 1, y is going to be e squared, and e is about 2.7. So it's like 2.7 squared, so you know it's flying up here somewhere. So the exponential curve is going like this. Now these two curves only intersected here at the point 0, 1, but the instructions for this says figure out between x equals 0 and x equal to 1. So when x is 1, we're stopping right here. So here's our little elements of area. You see them? So what's our integral going to be? Evaluate from
0 to 1.
Yeah, they told us already. 0 to 1.
E
to the 2x
minus 1.
minus parentheses 1 minus x. Be really careful there. dx. Thank you. All right. Not too bad, is it? No. Okay. All right, let's go with a couple of homework questions that were given to me prior to class, and tomorrow is review for the test day. So bring in that homework and let's look at it. All right. First one that I'm looking at is problem D, and this is from homework 12. And let's see what's happening here. Would everybody say if you integrate e to the 7x, you get e to the 7x 1/7 times it? Yep, your u is 7x, so du is 1/7. Okay, du. All right, so that's good. And then you put in your upper limit minus your lower limit. And then I don't know what happened from there. So you had 1/7 e to the 14th minus 1/7 e to the 0. Whose paper is this? Yeah. Did you take care of e to the 0? What's e to the 0?
1/7.
Okay, so you had 1/7 e to the 14th minus 1/7,
Yes.
and that didn't work.
But Carrie says I'm off by
Yeah,
a
like two
couple of
decimals.
It should be 0.47.
Six, I have point
Oh.
47.
So something happened in your calculator here. By the way, it might be easier if you factor out the 1/7 and do e to the 14th minus 1 and then divide by the 7. So let's see here. E raised to the 14th, subtract 1, divide by 7. Yep, looks like somewhere. You might have rounded and rounded way too many times. Keep all your answer in there till the end. It looks like it's going to be 0.47. Okay, so your process was totally correct. That was good. Okay. All right, that takes care of that one. That was easy to answer. I think there was another integration problem. Let's do those real fast, and then I'll come to the others. All right, this is on homework 11. 2x cubed minus 3 squared dx. Oh, I need to do this in big. All right, this is homework 11. Let me just rewrite it. The integral of 2x cubed minus 3 quantity square dx. All right. Where's the rest of your work on that?
That's pretty much all I got to. Like, I couldn't figure out how to integrate it, and like it wouldn't match up.
Okay, say that a little louder.
It wouldn't match up. Like when I looked from that.
When you looked both ways, it would not match up. Perfect. So that should have alerted you, I need to figure out something else to do. Okay, her comment was, I call u 2x cubed minus 3. And I got a u squared. du is 6x squared dx. This is where you had to look. Here you only have a dx. Here you've got a 6x squared dx. The only thing that can happen is matching with numbers and u's, and that's not going to work, is it? All right, so that is not the appropriate method for this problem, all right, because it doesn't match up. So forget that idea, it didn't work. All right, is there anything else you can do to this integrand to help yourself? You can square it. Try simplifying it when it doesn't work. So let's try squaring it. So if you square this, you're going to get 4x to the 6 minus 12x cubed plus 9 dx. Just multiply this out, squared it. And now when you look at it, could you integrate this term by term? Yes. So it doesn't mean that you can always jump on u substitution. You can get there, but it may not match up, so you got to go look, is there something else I can do to the problem? All right? Let's see what other question you had. Okay. This was problem G from the same exercises. You had an x squared plus 1 over x, and it looked like you were trying to make a u up in the numerator, and
I tried the denominator, it worked that way.
okay, and so none of those are going to work for you, right? Because when you took the derivative, the x is up in the numerator, and you needed a 1 over x. All right, so that's where you looked and you were sad again. All right, so then you come back, and when you look at that expression, you have an improper fraction here. You have two terms over the same denominator, and there's an x squared. So let's look for a way to simplify it. You got an x squared over x plus a 1 over x. So you are simplify. So then you can smile about it. All right, so x squared over x simplifies to x. So you got x plus 1 over x dx, and now you can just integrate term by term. So your u substitution did not work. You're sad. Go look and see if there's a way you can simplify the expression. All right, is that good, everybody? U substitutions do not always work. Okay, let's go to the next example. And this is on exponential and log functions, and we're on problem number 4. Okay, we have a radioactive element has a half-life of 6,000 years. Imagine a sample that's so old that most of its radioactive atoms have decayed, leaving just 3% of the initial amount. How old is it? You have 3% of the initial amount. Anybody see anything wrong with this? The future amount is 3% of the initial amount. That looks good to me. And where'd you get that negative 0.05? No, you can't think that. Let's see here. You're wanting it to be that way. That's a growth rate. That doesn't mean half-life is number of years. All right, so you started out with just shampoo, right? As a solution. All right, the information is that you will have 1/2 the initial amount when t is equal to 6, right? 6,000 years, half the initial amount. So that will give you information to solve for r. So 1/2 p sub 0 equals p sub 0 e to the r times 6, and that will allow you to solve that for r. Okay, so 1/2 p sub 0, you're going to, and if these p sub 0s bother you, it doesn't matter. Put 1,000 in there if you want to. It would be 1,000, and over here you'd have 500. Or you could have 100 and you could have 50. It's still going to work out the same. P sub 0 is just a number. So if you divide by that constant p sub 0, you get 1/2 equals e to the r times 6, 6r. What kind of equation do you have here? Exponential. What do you need to do to get to the r? Take the natural log of both sides. And so we get the natural log of 1/2 equals 6r. So r then is natural log 1/2 divided by 6. Let's get that much done right. Natural log of 0.5, divide that by 6. And so r, which you used as a negative 0.5 incorrectly, is negative 0.115525. I don't know how many places you need to take it so WebAssign is happy. Give your answer in thousands of years correct. I would keep all that for r. So now once you have r, you're ready to go to the next part of the problem. Does that get you going again? All right. Everybody good? Was that the last one on that? Okay. Organize your questions for tomorrow. Bring your work. That helps me. And then we'll talk through the material that's on the test. Work, work, work. Okay? Have a great day.